Assalamu alaikum. My name is Farooq Muhammad Aliu from King Fahd University of Petroleum and Minerals, Computer Engineering Department. I'll be presenting a course project for the course Network Design, COE 546, titled Man in the Middle Attack, a Detection and Prevention Technique in Fog Computing. Course is being taught by Professor Tarek Sheltami. This is the content of my presentation. Well, let's get on. Fog computing or edge computing devices are devices that are placed physically closer to the end user in order so that they process data on behalf of the cloud in order to reduce latency. This figure shows how the fog device is. It can be seen that the fog device is between the end device and the cloud. So in sometimes it performs operation on behalf of the fog cloud system. It can also solicit for services from other fog devices. Okay, this is another scenario for the application of fog devices. You can see we have the IoT devices in the figure here, and we have some fog in the fog layer. We have some few fog nodes which can provide services to the IoT layer when they can't provide the service directly. They get the information from the cloud. So why are we interested in security of fog systems? See, the fog devices are used to process a lot of data in order to reduce latency. As such, they process deep personal information like medical history, medication, person's state of health, real-time data from remote controlled cars and drones. They also process other crucial information like speed, direction, and destination of vehicles. Now, suppose you have a man-in-the-middle attack. It will be very dangerous given the fact that the adversary has access to information traversed in the network. This attacker can do whatever he so wish with the information. Furthermore, traditional detection techniques are not possible because you have a certain threshold for the latency, because you want the fog network to have shorter response in contrast to the cloud. Furthermore, there may be other constraints like energy or battery. In cases where the batteries you have battery powered fog systems. Therefore, we need an energy aware system that can allow us to secure the fog system. So in this project, we started with the aim to determine a cost-effective technique to detect and avoid man-in-the-middle attack for fog layer networks, as per this picture is concerned. Okay. Our objectives is to obtain cost-effective technique to reduce for detecting man-in-the-middle attack, as well as for preventing man-in-the-middle attack. Then we compare the system with those in the literature. Okay, key problem is that there is little work being done in fog computing security as at now. So it will be difficult for it is difficult to find any proposed system for man-in-the-middle attack that we can compare our results with. However, several work has been carried out in IoT, in security in IoT. Most common way for preventing man-in-the-middle attack is to encrypt packets as they move across the network. Once they reach their destination, they are then decrypted, and you have integrity and confidentiality. However, the aforementioned solutions have not been tailor-made for fog computing. They are designed for IoT, so they may not have constraints with regards to latency. So detecting a man-in-the-middle attack is another part of our project here, and it's based on the literature. It depends on the kind of attack. So in this case, we are detecting man-in-the-middle attack, and it solely hinges on observing the behavior of the nodes in the network. By nodes, we mean fog devices which communicate with one another, the cloud, and the IoT devices. Since man-in-the-middle attack does not destroy the packet, this makes it more difficult to detect the attack, because if we know the total number of packets and later we realize the number of packets has dropped, then we know something is happening. But in this case, packets would eventually reach a destination in man-in-the-middle attack, in a wormhole attack, and wormhole attack, which is also a variant of man-in-the-middle attack. So Aziz and his colleagues proposed a system for detecting man-in-the-middle attack based on time of arrival of the of the packets. However, in this kind of system, you need a well-synchronized network. Some authors also propose a MAC layer solution, in which in their case, they applied it to wormhole attack, which is a variant of man-in-the-middle attack. The system takes advantage of context. What we mean by context is the inability of the attacker to comprehend how the network works. Usually, a man-in-the-middle attack will just make a copy or alter the packet and then forward it to the destination. However, if you have a network with some special packets that are not supposed to be transmitted to the final destination, that should be dropped along the way, and they were not dropped. So see, the attacker now is out of context and therefore can easily be fished out. Also, we have another technique from the literature where the attacker's ignorance is a problem, is a way of finding the attacker. For example, in this paper, cited 10 in our reference, what they did is they have a packet with a secret question, which is then encrypted and forwarded to the expected node as a form of interrogation. So the expected node is the suspected node will then reply to this sender with after doing some calculations with S, and then it will reply to the sender with the results. The sender would also do the same computation on its side, and then it compares the two results. For an attacker that doesn't know what to do with the packet, then he may reply the packet or would send an acknowledgement, which is also out of context. Well, we found a true system that combines internet intrusion prevention system and intrusion detection system called TrueLink. It uses two phases. It uses roundabout phase for intrusion detection, and it uses authentication phase for intrusion prevention. In roundabout phase, what it does is the sender and the receiver exchange nonce. This time that is required for the exchange, it has a very high time constraint, and if a node is not able to exchange to send its nuance at a certain period of time after receiving nuance from the sender, then it is assumed to be an attacker or a potential attacker. The authentication phase, which is used for the IPS, is the sender and the receiver will exchange sign messages, thus mutually authenticating themselves as the original source of nuance sent during the roundabout phase. So the a node that has no signature can easily be fished out. So in summary, what we learn from the literature review is that we can detect man-in-the-middle attack based on change in the content of a packet, since some nodes exhibit packet modification as part of man-in-the-middle attack payload. Another thing is whether packets are being copied or they are being modified. What we are bound to get is that there is always a delay which can be detected. Finally, the direction of the packet may be changed in such cases as wormhole attack. Rather than the packet going to the original sender, it will find itself in somewhere else in the network with another receiver. So this is our proposed system. The proposed system consists of an IDS node which is surrounded by sensor nodes in one hop. R is the range of the sensor node, the IDS node, as well as the sensor nodes, while X is the distance between the sensor nodes. This arrangement will allow the system to have one sensor, at least one IDS node for a set of sensor nodes one hop away, as shown by the figure by this side. So we found that the relationship between R and S should be that X is equal to R times root 2 over 2, just so that we don't have interference between one group of nodes and another group of nodes. So how does the proposed system works? Well, what happens is the IDS node obtains an AES key, because for intrusion prevention we are using AES encryption, advanced encryption standard, which is the most used encryption system in information security. So the IDS node obtains key from the cloud using Diffie-Hellman Hellman key exchange. From then on, all fog nodes will obtain their key from the IDS using the same technique of key exchange, i.e. Diffie-Hellman. After every T discovery, the IDS node investigates nodes one hop away from it, as shown by this figure. It will investigate the nodes one hop away from it, and it will investigate each node by sending an IDS packet with an integer. It expects the fog node to decrypt the IDS packet, multiply the integer by 2, and then encrypt the packet and then send it back to the IDS. On receiving this packet, the IDS will then check the round-trip time of the packet and the resulting integer payload integer from the fog node. Then it compares it with its own values to see what the content is. So we have this algorithm which helps us determine how the proposed system will decide what type of attack is being made. The system has a threshold for timeout and has a threshold for time allowed for real packets. Any packet that exceeds that time, even after being received, it will be assumed that it is received from an adversary node. So the IDS during the interrogation period, T discovery, it sends this packet one-on-one, one-to-one communication in a unicast to each of the sensor nodes. Then it waits for a reply from each node, and it calculates the round trip time. So based on the round trip time, the node can now check. The IDS node will now obtain Y from the received packet, and then it can now check if IDS packet is null, that is, if IDS packet is not received, and we have reached timeout, then it's possibly a wormhole attack. Maybe the packet has gone somewhere. If our round trip time is is greater than the allowed time, but it hasn't reached timeout, then that means we have received a packet, but there is high chance that it has been altered. However, if we received a packet well within the time, but the reply payload is not an integer multiplied by 2, then we can, to a certain degree, think that the attack is modification type of man-in-the-middle payload. Finally, if none of this were true, then the node is not compromised. So latency, then we use this technique to test for latency and energy consumption of the nodes in using OMNET++. So we got energy. As you can see, node number 6 is the IDS node as shown in this figure, and it has the largest energy consumption of all the nodes in the corner. You can see 0 to 10 and 12, which are 0 to 10 and 12. As you can see, the fog node consumes more energy, while the while the other nodes have a little bit less energy. But you can see that um, the node 12 has more energy consumption than other non-IDS nodes because it's in the center of the network, and therefore it uh, it gets involved in forwarding packets to their destination as often. These are nodes. This is another set of nodes which also show the same behavior as the graph as the previous graph. You can see that node 1, 5, 7, and 11, 1, 5, 7, and 11 also show similar behavior. Those nodes inbound have consume more energy, and those nodes at the border consume less energy, and the fog node consume more energy compared to them all. So we also investigated the latency with IDS and encryption, without IDS, and uh, without using IDS, without using IDS, and without using any encryption. From our results, you can see that the mean for the latency of all the nodes is always very close values. That's why you can see graphically based on the position of the nodes. These are the nodes at the far end. The ones with the zeros are the fog nodes, and this is using the baseline, which is the one without any encryption. You can see that there is no difference. That's why we have to present it in a tabular form to actually see how close these values are. We also try to see how the fog node, how long it takes the IDS node to find an attack and to truly identify it with the right category. The fog node is able to identify all attacks correctly, and it takes this much time to know for sure whether the node is an intruder or not. This is the time when the node is compromised. This time here is when the node is compromised, and this is the time when it was discovered. The reason why we have late discovery is because the discovery time for our simulation is 2 seconds, and we have 0.5 seconds until the IDS node is able to figure out the attack. So in conclusion, we can say that an IDS node, an IDS IPS system is investigated, and we were able to use AES encryption for intrusion prevention, and intrusion detection techniques are used to detect attack if the attacker has managed to obtain the key somehow. And we found out that we developed the system in such a way that each node interrogates the nodes one hop away from it and check for content, context, or time of arrival in order to deduce whether it's an eavesdropping attack, a modification of content attack, or a wormhole attack. Also, you can see from the results here that the latency of the system the latency of the system has not been affected that much. You can see the system with the system latency here is when we subtract it from the system without any security layer, you can see we have 0.04. So that's why we said the latency for the system with our implementation is 40 milliseconds. Therefore, it can still be used for real-time applications and of course for some industrial applications too. Thank you for listening to this presentation, and these are some of the papers I cited in this presentation. Our OMNET code. This is the OMNET CC file where you simulate the behavior of all the nodes. This is the network description file. For the network, we included all the settings for the network in as parameters in this place. From here you can see that we set the number of nodes in rows and columns, a number of ports for each node, size of packets, transmission power, reception power, processor clock cycle, transmission reception. We also check this is like a switch to turn on attack and turn it off. This is a switch to turn off IDS and turn it on, so that we don't have to write another code for different settings. We have the channel with these specifications. So basically our transmission, this is how the topology is built. So basically this is our transmission, this is our node. We use parameters from microcontrollers and from other research papers on encryption and decryption of AES, and we also check the literature on parameters for wireless HART. Wireless HART is one of the well-known IoT protocol for industrial application. So we can run this and see what is the so now the system is good to go, and you can start running it. We can speed it up to we can speed it up to 2 seconds. As you can see, attacks have already shown themselves, and as you go, we can be seeing messages on lack of context, wormhole attacks. We can stop it here. So from here you can see RTT means return time. This message we put it there to tell us when we have a copying attack. Lack of context, probability of wormhole attack at this time, when node 9 sends to node 3 a message and it receives the wrong answer in the message. So we use we randomize the attacks. If you can see from the code, we use Poisson distribution to randomize the attack so that each node can make a different attack, as you can see here. So, and clearly you can see the IDS nodes are able to find out about these different attacks and even classify them. You can see packet is lost here. You can see perpetual forwarding means the node is just exhibiting wormhole attack and taking the without returning the packets to the rightful owner. Lack of context attack, when the node has no idea of what to do with the packet received. Thank you for watching. Have a nice day.